Our next speaker is Iqbal Mohomed from IBM Research, who's going to talk about self-driving Lego Mindstorms robots, which is kind of continuing the theme from the previous talk.
Hi, can you hear me? Cool. All right, good morning, everyone. So as you can guess, can people hear me? Yes? Okay. Hello? Okay. Cool. So good morning. As you can guess from the title, I'm not going to talk about some real research project that I'm working on at work. Rather, I'm going to talk about a hobby project that I've been doing, which is building a self-driving Lego Mindstorms robot. So how did this come about? This was really inspired from a blog post on Hacker News by a guy named David Singleton, and he was taking Andrew Ng's machine learning course, and he did a really cool project where he hacked some Arduinos to control an RC racing car, and he used some of the code from the course for machine learning. He combined Java, Octave, and a couple of other scripts to build this self-driving RC car. And when I first saw that, I had a little bit of disbelief. I was like, it can't be that easy to build this thing. And my disbelief, I was like, let me try this out and see if it could actually be that simple. And it turned out to be true. The system that I built is almost like a simplification of the work that David did, so it's like an independent replication of his work. It's only 300 lines of Python code, and it's available on GitHub, and if you want to take a look at it, I highly encourage it. In fact, I highly encourage, this was a really fun hobby project that took a couple of weeks, and if you have some time, I'd recommend doing it. It was a good learning experience. I used the Lego Mindstorms system for the physical build of the robot, and that helps to simplify part of the process. So this is the robot, the way it looks, pretty small. It's a two-tracked robot, so there's independent motors for the left and right track. So the differential drive, I guess, is the term. The interesting thing is there's an Android camera phone mounted in front of the robot. And that lets the robot see what's in front of it, and it can move around. So this is the robot on a track made from 8.5 by 11 printer paper, so not very sophisticated, just a track in my living room. And on the right-hand side, you can see some of the views from the camera of the robot. And again, the top one sort of is an instance where you should go forward, and then the other ones are like when you should go left and when you should go right. And when you first look at this, you're thinking, or you might think, let's just throw regular computer vision at the problem. So let's use OpenCV or something like that. And it turns out that there's a different approach. This idea of using an artificial neural network approach. And this was actually studied in academia in like a proper research project a long time ago in 1993 by some researchers at CMU, where they actually used an artificial neural network to create this learning algorithm called Alvin. And they actually drove a car and it went up to like 55 miles per hour just using computer vision. So it's far away from the Google self-driving cars that are here today, which use lots of sensor information, laser telemetry, and so on. This was just using computer vision, and it works. So the way my self-driving robot works is it's a three-step process. In the first step, you have to collect training data that you're going to use to train this neural network. That involves a human basically driving using a keyboard the robot around the track. And you collect both the command that the user pressed, so for example, forward, left, or right, as well as the image that was seen from the eye of the robot at that time. Once you've collected some number of samples, you can then use standard machine learning algorithms to train this neural network, which takes some time. It can with only 10 runs of the robot, it took an hour to train the neural network on my home PC. So that part is a little bit slow. Once you've trained the neural network, you can go into self-drive mode. So in self-drive mode, the robot basically just takes camera images, activates the neural network, and then drives around. And even if you change the track, it can still, most of the time, figure out what's the right thing to do. So without further ado, let me show you a quick video of this thing in action. Oops. So you can see that the robot is moving in spurts, and that's nothing fundamental. It's just the way I built the robot. There's like a 3-second sleep between every action, and the reason that's there is not because it takes so long to activate the neural network. The neural network activation is actually pretty fast. You gotta wait for the robot to stabilize and for the camera to stop shaking. Otherwise, you're gonna get blurry images. So you can see it took that corner. So it was a really fun process seeing this in work, in operation, because it's not 100% foolproof. It works 2/3 of the time. It goes through the whole course without any problems. 1/3 of the time it might get stuck somewhere, and it's still pretty shocking. Like every time it made corners like that, you were like, is it going to do it? It did it. Okay, so let's move on. So for the remainder of the talk, I'm gonna give you a bit of an overview of what I did, a bit of a tutorial. So if you wanted to do it yourself, you could use it, use these steps. I'm going to talk about the physical construction of the robot, some interesting things that I learned. I'm going to then talk about a couple of Python libraries that I used to make this thing work. Specifically, I used the NXT Python library to control the Lego Mindstorms motors. I used the Python image library, just like Byron before me, to downsample the images that I was getting before feeding them into the neural network. And finally, I used the PyBrain library for the neural network stuff. So a bit about Lego Mindstorms, if you're not familiar with it. It's basically, the heart of this thing is this NXT brick, which is in the center. It's a simple microcontroller which can take in a bunch of sensor data. I'm not using any of the sensors in the case of my application, but there's a bunch of touch sensors, color sensors, ultrasound sensors, and so on. The other thing is you can control motors with this thing. And the Lego motors are really nice. They're interactive servo motors, so they give you a high degree of accuracy, up to 1 degree, as they state, for controlling the position of the motor, and you can find out what the position of the motor is as well. In terms of the holder mechanism, so Lego has this really nice program where you can define these objects. So I created an STL file, and it's also available, so you can use the same holder mechanism. In terms of the physical build process, this was the most challenging part, because I had to make sure that the phone could go in and go out easily, and it had to be secure. So it turned out that this was a nice design. Those L-beams that you can see, the 2 L-beams at the top, they sort of move because they're using these frictionless pegs. And since it's plastic, the plastic can bend a little bit and the phone gets nice and snug. In terms of the way the whole thing is structured, there's the Lego robot that you can see on the right-hand side. There's 2 core components to it. There's this NXT brick, which has 2 ways of communicating. It can use USB, but then that's a problem because your robot's going to have a wire running through it. The other alternative is Bluetooth, which is the one I end up using. The Android camera phone basically communicates with the PC via Wi-Fi, so pretty standard stuff. It's hooked into my home wireless network. So now a little bit about NXT Python. It's pretty intuitive. I don't want to throw a mountain of code at you, but I just want to show you how easy it is to make this thing work. So there's like the first command, find one brick, establishes a connection to the NXT brick. You create a motor object that corresponds to one of the 3 ports that you have, and then you just say turn. And that's it. You can specify the power. So in this case, I'm saying go forward 100% power and turn for 360 degrees. So that should do 1 rotation. So that works really nice in theory. The problem is when you're a software person and you start dealing with hardware, you realize hardware does a lot of weird things sometimes. So there's issues with respect to accuracy. The way NXT Python works is it doesn't load the Python code onto the NXT brick itself. Rather, the Python code runs on the PC, and then it uses Bluetooth to communicate with this brick interactively. And there's a latency problem. So if you were connecting your NXT brick to your PC using USB, you're going to get a much better accuracy when you do these turn commands and so on. However, when you're using Bluetooth, you're going to get a slight delay. So for example, when you're doing a turn, you might get 80 degrees of incorrectness, which is pretty bad. So that's why there was a little bit of trial and error setting up the parameters for my specific robot. If you try to do this yourself, you might have to play around with the parameters yourself. The other thing that was a little bit challenging is when you have 2 motors, getting them to run in a synchronized manner, that's a little bit challenging. So the nice thing is NXT Python has a synchronized motor class that I was able to use. There's a little bit of trickiness with respect to how you set up the leader and the follower and the turn ratios and so on when you want this thing to turn, but that wasn't too bad as well. Now going to the images, I end up using a free app on the Android phone that just let me grab the images via HTTP, and then in order to feed these images into the neural network, they had to be downsampled and so on. And so I had to make them grayscale and I had to resize them. And that's all the code there is to actually do all of the image processing, which I think is fantastic. As a Python user, I'm blown away sometimes when I see how little code it takes to do things that are pretty complicated. So for example, to convert this thing into grayscale, it's just like a single convert command that does the thing and a resize command. That's really it. Now, in terms of the neural network, there's a lot of stuff in this area that I can't really cover in this talk. I'm going to give a very high-level overview of what's going on. If you're interested in learning about neural networks, because they're really cool, you can take a look at Andrew Ng's machine learning course, which is available on YouTube, and it's available, I think, on Coursera as well. The way this thing works is first of all, it's doing it's a multi-class classification neural network. And it's not predicting one thing, it's predicting 3 things. So at the very right-hand side, you can see 3 output units in this neural network. These things correspond to the 3 actions that the robot takes. It can move forward, it can move left, or it can move right. So the idea is that looking at the image that's on the left-hand side, given that image, or rather looking at a vector of the grayscale valued of the images, which is going in the input layer, the first layer of the neural network, what should be the output? And your training is essentially considered supervised learning. That training data gets fed into the neural network, and then at activation time, when you see an image, what's the right thing to do? That's what the neural network is figuring out. It's an instance of you can think of it as a functional black box that's doing a nonlinear classification. That's what's going on. So again, I've sort of butchered what neural networks do, but if you don't know what they are, then hopefully that gave you some sense of what these things do. Setting them up in Python using PyBrain was ridiculously easy. I'd never used PyBrain before this project, and I was a little bit blown away by how easy it was. So to actually create the neural network that I showed you, it had 10,000 input units, it had 64 hidden units, and 3 output units. It's literally 1 line of code that lets me set up the neural network. Now, collecting the training data for this thing. This was really fun. It was basically me and my wife just sitting around the living room driving this thing, so on the keyboard. Sometimes you would get it wrong as well, where the robot would crash, and we had to discard those samples because we don't want the robot to learn our bad behavior. And the way the thing works, again, the code is pretty self-explanatory. It's a three-step process. You grab an image, then you accept a command from the user, which is basically the action that they want to take, and you then record the action as well as the image at that point in time. Once you have this data, you got to train your neural network, and again, it's ridiculously simple. They have this supervised data set class. You instantiate that, and then you add samples. So every single instance that you recorded, an image plus the action, that's a sample that you call add sample that fits into the neural network. There's a little bit of data munging that you have to do. It's not too difficult in Python. Essentially, all these things have to be like vectors of numbers instead of images or whatever. And then to actually, once you've added the samples to your data set, executing it, you just use this backward prop trainer, and it's like one line that does the training. This one line takes an hour to execute sometimes. So what I did was I made sure that the training was done separately. So all of the keyboard data collection was done separately, the trainer was done separately, and then the runtime was done separately. So there's like 3 separate programs really that are working. Activating the neural network is also pretty simple. The process, so this function that you're seeing over here, use neural network, it's taking a trained neural network as input as well as a downsampled image. So to activate this neural network, you grab the pixel data for this 100 by 100 image, you call the activate function on the neural network, and then you get a vector, which is basically the probability that it's going to be a forward, a left, or a right. And then whichever one is the highest probability, that's the action that you return from this function. In self-driving mode, you just put these things together that I described. You take a picture from the camera, and you process it. You use the function that I just showed you to activate the neural network and find out the command to execute at that point, and then you sleep and all over again. And you get your own self-driving robot. So that's it. Some more fun ideas that I'm thinking about exploring, and again, I encourage you to take a look at these things. I'd like to actually hook up this thing with an Arduino robot that I'm playing with. This thing actually has a very limited sensor on top of it, which is this compound eye sensor that basically consists of a couple of IR LEDs that are emitting IR light and 8 IR detectors. So even without any fancy stuff, I can put my hand and make this robot follow my hand. I wonder what I can do if I actually hook the sensor data that I'm getting from this compound eye to a neural network. I think that'll be cool. The other thing that I think has a lot of potential is getting a robot with a Kinect and processing the volume information from the Kinect with a neural network kind of a setup. I think that has some really cool potential. So in conclusion, I think I did a pretty sophisticated hobby project, because of Python. Otherwise, there's no way I could have gotten so much bang for my, limited amount of free time. I used the NXT Python, the Python image library, and the PyBrain library. And again, I was a newbie at all of them. So I think it was a pretty good experience using these things. In retrospect, I think this combination of hardware hacking that's going on these days, things like Arduino, things like Lego Mindstorms, combined with these new sensors that are available. So for example, all the sensors you have in a smartphone, things like a Kinect, and when you combine all of these powerful machine learning libraries that you have in Python, it really makes for some really cool possibilities. Some acknowledgements. Since this was a hobby project, this is not just a lame acknowledgement. Like my wife actually helped me setting up the living room track and so on, so I want to acknowledge her. David Singleton, because without his blog post, I wouldn't have even thought of this idea. So it was a really inspirational post for me. And Professor Andrew Ng of Stanford, who made all these courses available for free. So that's it. Any questions or comments?
And we're going to ask that if you have a question, raise your hand and we'll pass the microphone.
So when you're gathering the training data, did you try taking the images and then flipping them, and then likewise flipping the action so you could double your training set and preserve that symmetry that you naturally had?
So that's a really good point. I did not do that, but when I actually read the Alvin paper, I read the paper after I actually did this thing. It turned out that that's one of the techniques that those guys do in terms of generating a lot more training data. And what's interesting is in the case of Alvin, they have some really sophisticated algorithms which move the camera viewpoint and they process the image to generate a lot more training data. In the case of this Alvin robot, just by watching a person drive for 5 minutes, it can learn how to drive, so it's a really good idea. I should try this on this robot as well. Thanks.
I was just wondering what the effects of adjusting the number of hidden neurons are.
So that's a really good question. Neural networks are sometimes frustrating, in research because there's a little bit of black magic going on in terms of how do they actually work. I tried adjusting the number of units. If you go with fewer neurons, then it's sort of like accuracy goes down. I tried a small number like 8, it made training go faster, but ultimately it felt like the trade-off for accuracy was pretty bad. Like it would crash like half the time and so on. Increasing the number of units from 64 also did not seem to improve accuracy, and it just seemed like a waste. So it's a bit of a hokey, black magic kind of a number that worked. I tried different numbers, but again, that's what worked for me.
How many layers was your neural net? And could you describe some of the failure modes? And could some of them have been avoided by giving it the ability to back up?
Absolutely, absolutely. That's a really good question. So let me just have this slide up so that you can kind of see what was going on. This thing is a very simple neural network. It's got 3 layers, so it's just got this input layer. The way the input layer is working is just the image data is getting mapped to the input layer. There's this 64-unit hidden layer in the middle, and then the final output layer. Now, going back to your point, some of the failure modes of this thing, what would happen is the robot, when I say it only had these 3 constrained actions, it can move forward, it can move left, or it can move right. And again, the motors are running for a specific duration, and accuracy is a problem. So sometimes what would happen is the robot would overshoot, go a little bit too forward, and almost like land on a white piece of paper, and then all it can see is just white paper close by. And that's really no good. Like, what can you do in that situation? So I thought that if there was a spin command, that's the one I was thinking of implementing, like a spin 180-degree command or a spin 90-degree command, that might help the robot recover from that. When I started playing with that, the problem was, it could do something really silly, like sort of go backwards with spin. So, that was one of the problems I had. I think if you had another camera on this thing, that might also help you quite a bit, because then you would perhaps see more vision towards you. Or I think that's another.
Yeah, I was curious. You've got 64 hidden units, 100,000 visible units, so you've got 6.4 million weights there. I was curious whether you tried downsampling the image at all, and to decrease the number of weights and therefore improve.
Yeah. So it's really funny, right? People have made this comment: computers are getting really fast. And I mean, the image in this case, it's sort of like the camera images are also ridiculously big. Like the smallest image I could get on I have a Nexus S and it has like 5 megapixels or something. So even going to 100 by 100 grayscale was downsampling it quite a bit. I bet if you reduced it, it would still work out really well. In fact, going back to the Alvin paper, so I read the Alvin paper after I did this thing, and it turned out that they had a very low resolution image. It was almost like 30 by 30, and they were just grabbing the salient features. So I bet if you lowered it down, that would also help you with training time, or training time for the neural network. That would go much faster.
The other interesting thing, I'm curious whether you thought about doing like a convolutional net type thing where you break the image up into grids and you maybe still have the full resolution, but through multiple layers. Did you consider trying something like that?
Yeah, that's a good point. I should try that as well. Yeah. Thanks.
Okay, so I think we have now maybe time for one last question, if anyone has one. If not, I do have a quick question. With the new generation of boards that are coming out sort of in the $100 range that are not Arduino class, but that are actually sort of dual or even quad-core ARM boards, would it be possible to basically would those boards have enough power to do the entire thing mounted right there with a few sensors?
So, you bring up a really good point. Like Raspberry Pi is the one I think a lot of people are thinking about these days, and there's other similar class of boards. Absolutely, I think there's a huge potential. What's really interesting is a lot of folks are putting Linux or these kinds of operating systems on these things. And there's this open source project called ROS, the Robot Operating System, which is it's sort of like you can think of a pub-sub way of controlling robots. And I think some of those folks are looking at putting bindings for these smaller boards. And I think that has great potential. Because again, if you see, the problem here is you have a PC that's, has to be controlling this robot, like wirelessly. And if you had this functionality on the robot itself, you can do a lot. That said, at Google I/O last year, there was a session on cloud robotics, which is going in the other direction. So in that case, these guys from Willow Garage, they have this, I think it's almost $200,000 or $500,000, like huge robot. And they say that some of the biggest budgets that the weight of the robot really adds to its power consumption as it moves around. And in the case of this PR2 robot, they have, my memory fails me, it's either 2 or 4 PCs that they have running on this thing. So they're consuming power and so on for doing a lot of work. So they're almost taking this alternate track where let's minimize, just put actuation on this robot and then just communicate via like a really powerful data center that's communicating. So there's these two philosophies almost. I think for the hobbyists, this Raspberry Pi and some of these other things are opening up this really huge potential.
Thank you. So let's thank our speaker again.
Thank you.